Yes, so our last speaker before the lunch break is Aran Tattar, who I'd like to point out has been a very good sport and is giving this talk on rather short notice. Thank you very much for stepping in. Unfortunately, one of our speakers had to cancel last minute for good reasons. Aran will be speaking about weak stability conditions and chains of torsion classes. And yes, feel free whenever you're ready.
Yeah, thanks for the introduction and for the organisation of this nice conference. Yeah, I'm going to be talking about weak stability conditions and chains of torsion classes, and this is based on joint work in progress with Hipolito Treffinger. So yeah, our setting is going to be an abelian length category. This is the ambient category in the background. When I say subcategories or objects, always implicitly mean of this category A. And yeah, let's see what the background is. So in the 90s, Rudakov defined some stability conditions for an abelian category and showed that they induce hard and narrow sim-ham filtrations of each object. A decade later, Joyce generalized this to weak stability conditions and showed that in a similar way, they also induce hard and narrow sim-ham filtrations. Then around 5 years ago, Brewster, Smith and Treffinger showed that if you start with one of these Rudakov stability conditions, then actually you can obtain a chain of torsion classes from this. And Hipolito joined these things together by showing if you start with a chain of torsion classes, then actually you also can obtain a hard and narrow sim-ham filtration of each object. So this is nice. It's a nice commutative diagram. However, it is acyclic and all the information goes in one direction. And what Hipolito and I have been doing in this project is sort of trying to complete this picture a bit and yeah, try and make some cycles in this diagram from weak stability conditions to chains of torsion classes. So what I'm going to do in the next 8 and a bit minutes is flashily tell you about this diagram and some nice consequences of these red arrows. Okay, so what actually is a weak stability condition? It's a map from the non-zero objects of our category to this interval 0, 1 that is firstly constant on isomorphism classes and along every short exact sequence in our category phi, this map phi is either weakly increasing or weakly decreasing. And for completeness, let's remember that a Rudakov stability condition means that these weak inequalities are replaced by strict inequalities or equalities everywhere. So for a stability condition, you need that phi is strictly increasing, strictly decreasing, or constant along the whole short exact sequence. And by W stab of A, I'll denote the space of weak stability conditions on A. This is a topological space. I won't get into the details of that structure, but it does have a topological structure. And what's on these other nodes? We have chains of torsion classes. So, well, let's remember what a torsion pair is. It's a pair of subcategories T of F, T and F, such that there are no morphisms from T to F, and every object in our category can be built as an extension between objects in T and objects in F. And in this case, T is a torsion class and F is a torsion-free class. And we are concerned with chains of torsion classes indexed by this interval 0, 1, and sort of put this restriction on that T of 0 has to be the whole category and T of 1 should be the 0 subcategory. Both the whole category and the 0 subcategory are both torsion classes, so nothing too extreme there. And by special T of A, we denote the space of chains of torsion classes indexed by this interval. So yeah, it's no coincidence that this interval is the same one as the target of our weak stability conditions. To make all the theory work, we just need these to be the same totally ordered set, and we like this interval, so we've gone with that. Yeah, so how does one go from these objects to hard and narrow sim-ham filtrations? Package this together in a theorem. So each weak stability condition and chains of torsion classes determines a special class of objects called semi-stable objects, and induces hard and narrow Simham filtrations of each object. Informally, hard and narrow Simham filtration is a unique filtration whose factors are these special distinguished semi-stable objects, and moreover, they somehow sit in a decreasing way. I may be underselling this point a little bit. These hard and narrow Sim filtrations are quite important, but in the interest of time, I'm not going to go into them too much. Okay, so now I can describe how we go from weak stability conditions to chains of torsion classes. If we start with a weak stability condition phi and a point inside this interval, then if we consider this subcategory T greater than or equal to P, which consists of the zero objects and all objects in our category whose quotients evaluate to at least P through this weak stability condition, turns out this is a torsion class. So this was done by Bristol, Smith and Treffinger for stability conditions, and Hipolito and I have just generalized this to the weak stability conditions case. Similarly, one could replace this greater than or equal to with just a greater than and obtain another torsion class, and then by ranging this over this P over the interval, one obtains two different chains of torsion classes. And it's nice that this map preserves the semi-stable objects and the hard and narrow Simham filtrations. So this is what I meant about this diagram on the first slide being commutative. No matter which way you go around the hard and narrow Simham filtrations, you end up with the same ones. And now we can describe how we go back from chains of torsion classes to weak stability conditions. If we start with a chain of torsion classes eta, then we consider two maps. One, omega sends an object y to the supremum of this indexing set such that y belongs to the torsion class at these of these indices, and dually mo of y, which sends y to the infimum of these indices such that y belongs to the torsion free class of that index. These are both weak stability conditions. And again, everything works out quite nicely. The original chain of torsion classes eta and these weak stability conditions mo and omega all have the same semi-stable objects and hard and narrow Simham filtrations. So there's not a unique or canonical way of going from chains of torsion classes to weak stability conditions and vice versa. We sort of have two choices in each direction, but they all always have the same semi-stable objects. And it turns out this is actually an equivalence relation to have the same semi-stable objects on both the space of weak stability conditions and that of chains of torsion classes. And if we quotient out by this equivalence relation, then we have that these topological spaces are homeomorphic. And yes, this has some nice consequences. First of all, we have a nice description and construction of the right-hand side, this chains of torsion classes up to equivalence, which is a completely algebraic thing. We're just talking about torsion classes. So we have an algebraic interpretation of these weak stability conditions or equivalence classes of, which is something that's not clear from the start. We can identify some subspaces of these topological spaces. For example, the total weak stability conditions. So these are weak stability conditions for which every indecomposable is semi-stable. These correspond precisely to chains of split torsion classes. And we can also study topological properties of this space. So this final bullet point is intentionally vague as we're still writing some things up. And I'd also like to say that this length assumption on our ambient abelian category, this was here for simplicity in this talk. It can be relaxed, and one can instead put a finiteness condition on the weak stability condition in chains of torsion classes. And to end, I'd just like to give you an example. So it'll be the largest example I can draw, which would just be the A2 quiver and the small module category thereof. So on the left-hand side, we have the posets or lattice even of torsion classes, and then this space of chains of torsion classes up to equivalence on the right-hand side is So, and sort of a quick way to describe how one goes from the left-hand side to the right-hand side is that every sort of path of length n-1 in the lattice gives you an n simplex in the space of chains of torsion classes. And I think that's all I want to say. Yes, on the last slide there are the references. Yeah, thank you.